In this video, we're going to go over section 4.2 from our textbook, which goes over the second derivative and what that can tell us about the graph of a function. So first, let's look at these two functions. F of x is equal to x squared and g of x is equal to the square root of x. And these functions are defined on this interval here. And we see that the derivative of our function f of x is going to be 2x, and that'll always be greater than 0 on this interval here. And similarly, the derivative of g of x here is always going to be greater than 0 on our interval as well. And both functions are increasing on this interval. So here's the graph of f of x here and the graph of g of x, and as we can see, from 0 all the way to infinity, both of these functions are increasing. Now, if we look at these two figures on the right here, so this one is figure 2a, we see that the f prime of x, so the slope of our tangent line, is increasing, right? So all of these tangent lines here are increasing, and we can see that each one lies below the actual graph of f of x. Similarly, we have this graph g of x here, and all of our tangent lines are decreasing in this case, and every single tangent line lies above our graph, or in other words, our graph lies below each tangent line. This brings us to our definition of concavity. So the graph of a function f is said to be concave upwards on some interval if the derivative is increasing on that interval. So for example, this graph here, we see that the derivative is increasing on this interval, and a function is said to be concave downward on the same interval if its derivative is decreasing. So just like in this example here, we see that the derivative g prime of x is decreasing here, and all of the tangent lines lie above the graph. Okay. Now in section 4.1, we used f prime of x to determine when f of x is increasing or decreasing. So this implies that if we want to see if f prime of x is increasing or decreasing, we're going to need to use its derivative. So this brings us to the second derivative here. So if we have a function f of x, the second derivative, assuming that it does exist, is going to be the derivative of f prime of x. And so other notations for this are, so we have f double prime, you can say f double prime of x, or this here, and y double prime. So going back to the functions that we mentioned at the beginning of this section, we have x squared and the square root of x. Taking their derivatives, we get 2x here and 1 over 2 times square root of x here. And then to find their second derivatives, all we're going to do is take the derivative of their first derivative. Okay? So for f double prime of x, we just get 2, and then for g double prime of x, we get this guy here. And so notice, we're looking at the second derivative here. Well, we know that our functions are defined on the interval 0 to infinity, so x is going to be greater than 0. We know that our second derivative is also going to be greater than 0, or in other words, it's going to be positive. Now in this case, if our second derivative is positive, this tells us that our first derivative is going to be increasing. Just like how we saw in the last video, if our derivative is positive, then our function is increasing. And we just saw that if our derivative is increasing, then our function is concave up. So we'll say, in this case, f of x is concave up. Similarly, looking at our second derivative for g of x, for positive x values where our function is defined, we have that our second derivative is less than 0. So in this case, it's negative. So this tells us that g prime of x is going to be decreasing, just like how we saw If our g prime of x was negative, then our function was decreasing. So same thing here, we're using the second derivative to figure out if our first derivative is increasing or decreasing. And then we saw up here for our definition of concavity, if our derivative is decreasing, then our function is concave downward. All right, so this is our little summary of concavity, essentially what we just did. So if we have that our second derivative is positive, then our first derivative is increasing, and this tells us that our function is concave up. And then if our second derivative is negative, and this tells us that our first derivative is going to be decreasing, and then our function is going to be concave downward. So here are some examples of curves that are concave up, and then here are some that are concave down. Now we do have to be careful. We don't want to confuse concavity with rising and falling. A graph that's concave upward could be falling, rising, or both. And similarly for a graph that's concave downward. So here are some examples of concave upward. So here our second derivative is greater than 0 on this interval here. So in this case, our derivative is negative and increasing. In this case, our derivative is increasing from positive to negative, and it falls and then rises, and so on. So you can look at all of these cases when we have a concavity that's upward and then downward. All right. So let's look at this example here. What we want to do is determine the intervals on which the graph of each function is concave upwards and where it's concave downwards. So this tells us if we want to look at the concavity, we're going to need to find and determine the sign of the second derivative. So let's look at this first one here. We have f of x is equal to e to the x, e to x. We know that the derivative is just going to be e to the x. And so our second derivative is going to be the derivative of our first derivative. So this just becomes the derivative of e to the x, which just becomes e to the x. All right. And we know that e to the x is going to be greater than 0 for all x in our domain of all real numbers. So that's just a property of e to the x. Our range is 0 to infinity for this guy. All right, so if it's always going to be 0, so our second derivative is positive. It's always going to be positive. Then this tells us that our first derivative is going to be increasing, and therefore f of x is going to be concave up. Okay. So here is a graph of that. So we have that f of x is going to be concave upward for all x, concave upward for all the x values from negative infinity to positive infinity. And then we can see this shape here, concave upward. All right, now we're going to look at b here. So g of x is equal to ln x. So we know that the derivative of ln x is 1 over x. And so the second derivative of this guy is going to be the derivative of that. And so what we can do is rewrite this with a negative exponent. And so we get that our derivative is going to be using the power rule. We're going to have negative 1 come down in front. And then we have x to the power negative 1 minus 1, so negative 2. So this is our second derivative. All right. So we know that our second derivative is going to be less than 0 for all x in our domain. And we know that our domain of ln x for our natural log is 0 to infinity. And so for all numbers in our domain, this is always going to be negative because we have this negative out here. So our second derivative is negative, which tells us our first derivative is decreasing, and therefore our function is concave downward. All right. And then here is a sketch of that. We can see that our function is concave downward for all x values. All right, or in all x values greater than 0, so all x values in our domain. And lastly, we're going to look at part C here. So h of x is equal to x cubed. So h of x is equal to x cubed, so our derivative is going to be 3x squared. And then our second derivative is again going to be the derivative of our first one. So again, using power rule, we'll just get 3 times 2 times x. All right. Now we have 6x is going to be less than 0 for x less than 0. So this means for all of our x values that are in this interval, negative infinity to 0, we have that our second derivative is negative, which tells us our first derivative is decreasing, and this tells us our function is concave down. But it'll just be concave down on this interval here, because our second derivative, 6x, is going to be greater than 0 for x values greater than 0. So in this interval. And so then this tells us that in this interval, our second derivative is positive, which tells us our first derivative is increasing. And lastly, our function is concave up. All right, and so here is a graph of exactly that. We have in this region from negative infinity up to 0, our graph is concave down. And then at this point, at x is equal to 0, it changes to be concave up. And so actually, at this point here, x is equal to 0, the concavity changes. This is what is called an inflection point. All right, so that brings us to finding inflection points. So, like I said, an inflection point is a point on the graph where the function will be continuous and the concavity changes. And so it can be from upward to downward or from downward to upward. And then for the concavity to change at a point, the second derivative must change sign at that point. All right, and then something to recall here, we saw in section 2.2 that the partition numbers will identify the points where a function can change sign. So if this point here is an inflection point of f, then c is going to be a partition number for the second derivative of f. All right, so that brings us to this procedure for testing for inflection points. So what we'll do first, the first step is to find all partition numbers c of f double prime such that f is going to be continuous at c. Then for each of these partition numbers, we want to construct a sign chart near that number c. And then we'll see that if our second derivative changes sign at c, then we'll have an inflection point. And if it does not change sign at c, then there is no inflection point. All right, so let's do this procedure for this example here. First thing we want to do is find all of the partition numbers. So we know that we're going to need to find the second derivative of our function and find the partition number of that guy. So the first derivative of our function is going to be 3x squared minus 18x plus 24. And then our second derivative, we're just going to take the derivative of this guy. So we'll do power rule. So we get 3 times 2, so 6, and then x to the power 2 minus 1, so just x to the power 1. And then minus 18, and we know the derivative of a constant is 0. And then we're trying to find partition numbers, so where this guy is undefined or equal to 0. But since it is a polynomial, our second derivative is going to be defined for all real numbers. So now what we'll do is see if there's any way this guy is equal to 0. And we can see that that is the case when x is equal to 3. Okay, so just setting it equal to 0 and solving for x. Alright, so this will be our partition number for our second derivative. So we're cutting our domain into 2 regions, this here, because we know at x is equal to 3, our function can change sign. All right. So here is our sign chart. I got it already set up. So we're going to look at the region for this interval from negative infinity up to 3, and then from 3 to infinity. So we'll look at some test numbers in each of these intervals. The first number we're going to look at is 0 in the first interval. So plugging this into our derivative, we'll get a negative number because we have 6 times 0, which is just 0, and then minus 18. So we get negative 18. So this is negative. I'm sorry, we should have f of x here. Alright, so if that's negative, then f prime of x is going to be decreasing, which tells us that f of x is going to be concave down. Right, then looking at this interval here, we'll choose 4. And then plugging that into our second derivative, we will get 24 minus 18, so that's a positive number. So since our second derivative is positive, this means our first derivative is increasing and our function is concave up. And so we know that our second derivative at x is equal to 3 is also 0. So we can just put that there. So we just saw that at this point x is equal to 3, our function changes from concave down to concave up. So this means we do in fact have an inflection point. And that occurs at x is equal to 3. Okay, so plugging that into our function here so we can find our output value. We'll get 8. So we have an inflection point at 3, 8. All right. So something to note here, some more conceptual insight. So it's important to remember that the partition numbers for our second derivative are only candidates for inflection points. So the function f must be defined at that point x is equal to c, and the second derivative must change sign at x equals c in order for the graph to have an inflection point at that point. All right, so let's look at these functions, for example. In each case here, we'll have that x is equal to 0 is going to be a partition number for the second derivative, right? This will be defined everywhere, but in order for it to equal to 0, we need x to be 0, and this guy will be undefined when x is equal to 0 here. However, neither one of these has an inflection point at x equals 0 because, so our function f does not have an inflection point at this point because our second derivative does not change sign at that point. Okay, so that's the case for f of x here. And then for g of x, our function g does not have an inflection point at x equals 0 because g of 0 is not defined. So we can see this graphically here. F of x does not change sign at x is equal to 0. And then in this case here, g of 0 is not defined at all. Looks like we have a vertical asymptote at x is equal to 0. Okay, so that's just to emphasize that these partition numbers are only candidates for inflection points. All right, now let's look at this example here. All we're given is a graph of f prime of x, and so we want to use the graph of the derivative of a function f to discuss what the graph of f may look like. And then we will include a sketch of a potential graph of f given that information. Right, so what we'll do is split our graph up into different intervals where our derivative is increasing and decreasing. So as you can see here, our derivative is decreasing. Here it's increasing. Here it is decreasing. And then here it's still decreasing, but it's changing sign. Okay. So what we're going to do is break our domain up into these intervals. And just to stay with the color coding here, that's this region, this region, this region, and this one. Okay, so these are partition numbers that are breaking our domain up into these intervals. And we know that these are in fact the partition numbers because right here we have a horizontal tangent line at x is equal to -1. And then here we have a horizontal tangent line at x is equal to 1. So those are partition numbers. And then at this case here, f prime of x changes sign. So we have another interval here, another partition number at x is equal to 2. Okay, so what we're going to do is construct somewhat of an elaborate sign chart to include all of these intervals and essentially give us information on the derivative and the function of f based off of this graph here. All right, so we're going to look at this region. This one, and that's our last interval. So what I mean is we'll look at this graph here, which is the derivative of f, and we see that in this region from -infinity up to -1, it's decreasing. But we also see that all of our f of x values in this region are positive. Okay, so our derivative, all of our output values are positive, but this guy is decreasing. So positive and decreasing. Okay. So since our derivative is positive, our function is going to be increasing. And since our derivative is decreasing, our function is going to be concave down. Okay. So just keeping track of everything we've learned about what our derivative tells us about our function. Then f prime of x is going to be equal to 0 at -1. And just based off of this graph, we also see that we have a local minimum at -1. Okay. Now let's look at the interval -1 to 1. So in this case, we see that our derivative, all of our output values are still positive, but now in this case, f prime of x is increasing. So it's positive and increasing. So then that tells us that our function is going to be increasing in concave up. Now notice here we go from concave down to concave up. So that tells us that our function is going to have an inflection point at -1, because at this point our concavity is changing. Now looking at our graph, when x is equal to 1, we know that our output, so f prime of x, is equal to 3. And then just looking at this graph, this also is a local maximum at that point. All right, now looking at our next interval, 1 to 2 here, we see that our f prime of x is still positive, but it's now decreasing. So then that tells us that our function is going to be increasing in concave down. And since again our concavity is changing, it's going from concave up to concave down at this point, this is an inflection point. All right. Then we know when x is equal to 2 here, f prime of x is equal to 0. And we can just tell by this graph, since we're not changing from increasing to decreasing here, we don't have any local extrema. All right. Then looking at this interval here, 2 to infinity, we see that our f prime of x now has negative values and it's decreasing. All right, so if our derivative is negative, then our function is going to be decreasing. And if our derivative is decreasing, then our function is going to be concave down. And lastly, since our function is going from increasing to decreasing here, this point here is going to be a local minimum. Sorry, this should actually be a local maximum. Because remember, when our function goes from increasing to decreasing, we'll have a local max because our graph is behaving in this sense. So we're going from increasing and then now we're decreasing. All right, so that was how we can use the graph of our derivative to provide some information on our function f of x. Okay, so now we're going to get into the first version of curve sketching for this book. So this is the procedure to do so. And so what I mean by first version is that we're going to go over in more details, or I think there's like a final version in section 4.4. But in this section, what we're going to do is follow these steps. So first, we're going to analyze f of x, or a function. We're going to find its domain and the intercepts, so the x and y intercepts. Then we're going to analyze its derivative, so we'll find the partition numbers and critical numbers and construct a sign chart, and then determine the intervals for increasing, decreasing, and find the local extrema. And then we're going to analyze our second derivative, so we'll do the same thing that we did for our first derivative, but now for our second derivative, and this will tell us the concavity and the inflection points. And lastly, we will sketch the graph with this information. All right, so following this procedure, we're first going to find the domain and x-intercepts for this example here. So first step, we know that f of x is a polynomial. So this tells us that our domain is going to be negative infinity to positive infinity. Next thing we want to do is find the x-intercepts. So here's our function. And we know if we want to find the x-intercepts of our function, we're just going to figure out when this is true, when our function is equal to 0. So in this case, we can factor out an x cubed, and so we get x plus 4. So then this tells us that our function will equal 0 when x is equal to negative 4 and 0. So our x-intercepts are negative 4, 0, and 0, 0. Then to find our y-intercepts, what we're going to do is set x equal to 0, and solve. And so in this case, we get 0. Okay, so this tells us that our y-intercept is 0, 0, and then we actually already have that as our x-intercept as well. This is the origin. All right, so the next thing we're going to do is step 2. So we're going to analyze our derivative. We're going to find the partition numbers for our derivative and construct a sign chart. So we'll take the derivative of our function. So we'll get 4x cubed plus 12x squared, just doing a power rule. And remember, since this is a polynomial, it'll be defined for all real numbers. So we just want to figure out when our derivative will be equal to 0. So pulling out a 4x squared from both of these terms, we get x plus 3 there. And then this tells us that if this were to equal 0, we would need either x to be equal to 0 or x to be equal to negative 3 here. So these are our partition numbers. For our derivative. And this is also known as the critical numbers for our function. So this is where our derivative can change sign. And so our domain is broken up into the intervals, which I'll put here in our sign chart. Sorry, that threw me off. Negative 3 and 0. All right, so what we want to do is get some test numbers and see what the sign of our derivative is going to be in these regions. So I'll do that on the side here. Negative 4 is in our interval negative infinity to negative 3. So plugging this into our derivative, we'll get 4 times negative 64 plus 48. So this will be a negative number. So this tells us our function is going to be decreasing. Looking at the next interval, negative 3 to 0, we're going to plug negative 1 into our derivative. Right, so we'll get negative 4 plus 12, so this will be positive. And so our function is going to be increasing. All right, and then looking at our last interval, we'll plug in 1, and so we'll end up with 4 plus 12, so this will just be positive. So our function is still increasing here. Okay. And then we know that at these numbers, our function, or our derivative, is going to be equal to 0. And then since we saw that our function's going from decreasing to increasing at this point here, we're going to have a local minimum. Right, so our function kind of looks like this, going from decreasing to increasing here. And then at this point, our function is not changing from increasing to decreasing or vice versa, so we're not going to have any extrema there. All right, so the next step we're going to do is do the same thing, but now for our second derivative. So our second derivative is just going to be the derivative of our first derivative. So we're going to use power rule again. So we'll get 12x squared plus 24x. And again, this is a polynomial, so it'll be defined for all real numbers. So we just need to see when our second derivative will be equal to 0. We can factor out a 12x from both terms here. And so this tells us for this guy to equal 0, x either needs to be equal to 0 or x is equal to negative 2. So these are our partition numbers for our second derivative. Okay. So this breaks our domain up into these intervals. Remember, these are the intervals where our second derivative can change sign. So we'll look at some test numbers in these regions. So from negative infinity to negative 2, we'll look at negative 3 here. So plugging this into, sorry, this looks like a parenthesis, plugging this into our second derivative. We'll get a positive number. So our second derivative is positive. This means our function is going to be concave up. Then looking at our next interval from negative 2 to 0, we're going to plug in negative 1. So we'll get a negative number there. So in this region, our function is going to be concave down since our second derivative is going to be negative. And then from 0 to infinity, we'll plug in 1. And so we'll just get 12 plus 24, so this is going to be a positive number. So in this region, our function is going to be concave up. Right? And then we know that at these points, since these are our partition numbers, our second derivative is going to be equal to 0. Additionally, we see that our function goes from concave up to concave down here. So this indicates that we will have an inflection point, and we know that we have an inflection point when this guy changes sign as well. So we have an inflection point there, and we're going from concave down to concave up. Our second derivative is changing sign at this point as well, so we have another inflection point here. All right, now we can take all of the information that we found in the first 3 steps and sketch the graph of f. So in the interest of time, I did already provide the graph here and some points. So we know that our x-intercepts were negative 4, 0, and 0, 0. So those are where our x-intercepts are located. We also know from step 2 that we have a local minimum when x is equal to negative 3. So plugging negative 3 into our function, we get negative 27. So we have our local minimum here. All right. We also know that we're going to have an inflection point at negative 2. And so plugging negative 2 into our function, we'll get negative 16. So right about here, we have an inflection point. Our concavity is changing. So here we're going from concave up and then going in this direction, concave down. And we know that we have another inflection point at 0. And we know that when we plug 0 into our function, we just get 0. And we can see that the concavity is changing again. It's going from concave down to concave up here. All right, so that's how we would use everything we've learned to sketch a graph. And like I said, in section 4.4, we're going to go into more detail with graph sketching, which is going to include asymptotes as well. But for now, that's it for that one. And the last thing we're going to look at is this concept here, which is called the point of diminishing returns. So if a company decides to increase spending on advertising, it would expect sales to increase, right? Now, at first, sales will increase at an increasing rate and then increase at a decreasing rate. So the dollar amount, X, at which the rate of change of sales goes from increasing to decreasing is called the point of diminishing returns. Right, so we can kind of think of this as a local minimum value, right? So we're going from increasing to decreasing. Sorry, local maximum value. We're going from increasing to decreasing, and that's what this states here. This is also the amount at which the rate of change has a maximum value. Okay, so let's look at this example here. Currently, a discount appliance store is selling 200 large screen TVs monthly. And so if the store invests X $1,000 in an advertising campaign, the ad company estimates that monthly sales will be given by this function here, defined on this interval. So we want to figure out when is the rate of change of sales increasing and when is it decreasing, and what is the point of diminishing returns and the maximum rate of change of sales. So we know that the rate of change of sales is going to be given by the derivative of this, since this represents the monthly sales. So we'll find the derivative of this guy using power rule. So we'll get 12x squared minus 0.25 times 4 doing power rule, just going to give us 1. So we have x cubed here. And we know the derivative of 500 is going to be 0. So we just get this, and then simplifying a little bit, this is our first derivative. All right. And we want to figure out when our rate of change of sales is increasing and decreasing. And we just saw that to find when our derivative is increasing and decreasing, we'll use the sign of our second derivative. So taking the derivative of our first derivative, we're going to get 24x minus 3x squared. And simplifying a little bit, we can pull out a factor of 3x for both of these. We'll get 8 minus x. All right, so we'll do the same thing we did in the last example. We'll construct a sign chart to see when our second derivative is positive and negative, which will tell us when our rate of change of sales is increasing and when it's decreasing. So we want to figure out when this guy is equal to 0, because remember, this is a polynomial, so it's defined for all real numbers. And we see that if x were to be equal to 0, this would equal 0, and if x is equal to 8, this is equal to 0. So these are our partition numbers. And so this is breaking up our domain into these intervals. And remember, our domain is just from 0 to 12 in this case. So we'll construct our sign chart here. So we'll look at numbers in our first interval, 0 through 8. So just plugging 1 into our second derivative here, we're just going to get 3 times 7. So this is going to be a positive number. And so this tells us over this interval, our first derivative is going to be increasing. And then this tells us our function is going to be concave up. Similarly, if we were to plug in a number in our second interval, 8 through 12, this would be negative, this would be positive, so we would get a negative number here. So our derivative is going to be decreasing, and our function is going to be concave down. All right. We know that our second derivative is going to be 0 at this point. But then we see that our derivative is going from increasing to decreasing at this point. So this tells us we're going to have a local maximum value at this point. Similarly, our function is going from concave up to concave down, and our second derivative is changing sign. And so this tells us we're going to have an inflection point at x is equal to 8. All right, so this tells us that our rate of change of sales is going to be increasing on this interval and then decreasing on this interval. Now we want to figure out what the point of diminishing returns is. So remember, the point of diminishing returns is going to be the dollar amount x at which the rate of change of sales goes from increasing to decreasing. So it's the dollar amount x at which we have a local maximum. So this tells us the point of diminishing returns is when x is equal to 8. And then we know that our maximum rate of change also occurs when x is equal to 8. So our maximum rate of change is going to be 256 TVs. Additionally, we know that when x is equal to 8, our monthly sales is going to be given by this guy here. So plugging 8 into our equation, we get 1,524 TVs. Okay, so what this information tells us is that if the store spends $8,000 on advertising, our monthly sales are expected to be 1,524, because remember, our function n of x represents our monthly sales. And we also see that sales are expected to increase at a rate of 256 TVs per $1,000 spent on advertising. So when we spend this much on advertising, we're increasing at this rate here. However, after the point x is equal to 8, after this point of diminishing returns, we see that our rate of change starts to decrease. All right, so sales would increase, but at a lower rate. And lastly, I have a sketch here of our curves, our derivative, and our function. So as we can see, this curve here, we have a maximum value at x is equal to 8. And on this interval, from 0 to $8,000, our derivative is increasing. And in this interval, 8 to 12, it's decreasing. Similarly, we saw from our sign chart that for this interval, 0 to 8, our function is going to be concave up. And then at this point here, we have an inflection point where our derivative is now less than 0, and we see that our function is concave down. Okay, so that's it for this example.